want to thank you all for attending this session, and it's a real pleasure to be here today. I'm sorry that I don't speak any Turkish, but hopefully they'll have a good translation for you all. It's a real pleasure to hear all of these lectures on complementary and traditional medicine. As an ethnobotanist, I spend a lot of time studying traditional medicines. The topic I'm going to speak on today has to do with one of the greatest threats that we currently face in medicine, and that is antibiotic resistance. I'm going to specifically discuss the role that I think that traditional medicine, in particular from botanicals, will play in the future of the treatment of infectious disease. I was very pleased during the opening ceremonies to hear the words of Her Excellency, the First Lady of Turkey, also mention antibiotic resistance as an important problem that we need to look for solutions for. I'm going to give you some specific examples of discoveries that we've worked on in my own laboratory regarding different ways that we can use plants to overcome antibiotic resistance and restore the activity of our existing therapies. Antibiotic resistance is a major problem, not just in the US or in Turkey, but it's worldwide. Every week in the news, you see new reports of what they call extremely drug-resistant strains, or XDR isolates, and also multi-drug resistant strains. Bacteria can travel from person to person, from continent to continent, and they can carry these resistance characters with them. So we need new solutions. You can see on this first graph some examples of the rising trends in antibiotic resistance. And on the right, you can see the results of a recent report put out by the UK government. In this report, they estimate that today, around 700,000 people worldwide will die due to infections that are unable to be treated with our current antibiotics. By the year 2050, it is estimated this number will reach 10 million deaths per year due to untreatable infectious disease. One of the issues that has fueled this problem is not only the rise of resistant strains that have spread globally, but also we've really begun to fail when it comes to the discovery of new drugs. This is known as the antibiotic drug development pipeline void. We haven't had any new registered classes of antibiotics discovered since the 1980s. All of the antibiotics that have been introduced to the market since the 1980s have simply been small modifications to existing chemical structures. We need new types of structures and new ways of approaching these diseases. This also coincides with a shift in the drug discovery pipeline. In the 1990s, many pharmaceutical companies turned away from research on natural products, and they began to work on something called combinatorial chemistry libraries. These are man-made synthetic compounds that were then tested against many types of bacteria. They've tested literally millions of these compounds without success. None of these initiatives resulted in production of any new antibiotics. Now, I think all of us in this room can appreciate that plants are a logical place to look for new therapies. We've had a long history of the use of plants in medicine. Here are a few that you're probably familiar with. We've found plants such as willow to treat pain through aspirin, foxglove to treat cardiac insufficiencies, mayapple for cancer, and poppy for pain. These are just a few of the examples of important plants that we use across the globe. Now, this is a session on the words of Hippocrates and the value of ancient medicine, and I just wanted to note the timeline of historic medical texts that we have on record. These are the books that have survived. So beginning back to 1500 BC with the Ebers Papyrus discovered from Egypt, we have very clear records of plants used as a key part of the pharmacopoeia. Moving on to the works of Hippocrates and his school of thought, there are also a large large number of plants that are recommended, mainly through dietary intervention for the treatment of disease. And of course, there's the work of the famous Dioscorides, who traveled throughout the Mediterranean documenting all of these many medicinal plants and the ways that local people use them. In a recent report conducted by the Kew Royal Botanic Gardens in the UK, they found in the State of the World's Plants, we have at least 28,000 species globally that have been documented for their medicinal applications. This is out of roughly 400,000 species total of plants on Earth. Now, if you look into the scientific literature and investigate how many of these species have actually been studied in a rigorous manner in a laboratory, looking at their chemistry or looking at their biological activity, or even looked at through controlled clinical studies, this number is very low. So there's a lot of room here for the scientific community to explore and to better understand how many of these medicinal plants work. In my research group, we take a four-pronged approach to our drug discovery and research initiative. So this combines field work. This is a photo of me in northeast Albania, where I work with local people to document their traditional knowledge. We also bring our specimens back to an herbarium, which serves as a plant museum of sorts to store our specimens for hundreds of years. We then extract those plants in the phytochemistry lab, which is where we pull out the chemicals in the botanical material, study those chemicals, and try to identify them. And then lastly, we work in a microbiology and cell culture facility where we test these chemicals from the plants, the plant extracts and formulations, against a number of different antibiotic-resistant pathogens. Now, I often am asked, why do you work primarily in the Mediterranean? Well, you all know the Mediterranean is a jewel on Earth. It also happens to be one of the global biodiversity hotspots. In fact, these hotspots across the globe are very unique in that they have around 44% of all species of vascular plants are confined to these spots. In the Mediterranean alone, there are 25,000 plants that are native to the basin, and 13,000 species are actually endemic, meaning they can only be found in these regions on Earth. They're not found anywhere else. Some of the different collection sites that we work in, I mentioned Albania. We also work with partners in Kosovo and in Italy. And most recently, I've spent a bit of time around Sicily working on volcanic islands, looking at their biodiversity. We also collect plants in the US. Now, how do we go from 400,000 species down to around 500 species that we currently work on in my laboratory? Well, we use the lens of ethnobotany. Ethno refers to the study of culture and people. Botany is the study of plants. So we use the knowledge that local peoples have concerning their traditional medicine to really focus on those plants that might have some utility in the treatment of infectious disease. Other reasons that we work in the Mediterranean is that in addition to its high levels of biodiversity among plants, there's also an incredible diversity in culture and in language. And wherever you have linguistic diversity, there often is embedded within that a great amount of knowledge about the surrounding landscape or the environment. I just wanted to show some different photos of our work in different areas of the Mediterranean so you can get an idea about the different types of landscapes. So these are some photos from the alpine regions and the Shari Mountains in Albania along the Kosovo border. This is a place where local people grow most of their food during the warm months, and they ferment much of their food and store it for consumption throughout the year. Most of their medicine, I would say at least 90%, comes from wild medicinal plants that they gather during the spring and summer. Here are some examples of plants that you might be familiar with also here in Turkey. In the top photo, this lady is holding a sample of Cantarion, also known as Hypericum perforatum. In the Balkans, they make this with as an oil infusion in olive oil where it's left in the sun, and I know you also use it here. Now here's a different landscape. This is in Pantelleria. Pantelleria is an Italian island located just off the coast of North Africa, near Tunisia. And on this island there is no fresh water. And so they must use all of their resources of gathering the morning dew and what little rainfall they have to grow their different food plants. And they also use a lot of wild plants for both hunting and fishing. For example, there are many poisonous plants they use as fish poisons to catch fish. And they also use other plants such as this one of Daphne nidium to treat cuts and stop bleeding. In Kosovo, this is neighboring to Albania, we have, again, many of these similar medicinal plants. However, here, many of the villages are more closely connected and accessible because of the roadways that have been built into the country. And so here you also have a very active local market where many medicinal plants are sold and traded. This summer, I worked with my family on another island chain in south of Italy. These are my children. When they come to work with mommy, they have to ride the donkey with me and carry the plants down the mountain. And so on this island, this is a unique island chain full of many endemic species, also with a very rich history of traditional use. We also collected plants from under the water, seaweeds that were used for skin disease. Now, when we conduct these researches, we also take a number of important steps for ensuring that everything is done under the ethical purview of international codes of ethics. So this includes access and benefit sharing. So our work with communities is really about a partnership with those communities. Some of the things that we do with access and benefit sharing is to return the knowledge that we document back to local communities. This is sometimes done with workshops, or with the return of a book, or by training other students from different universities at my university and having scientific exchange both ways. Once these plants are collected, they're dried in the field and shipped back to my lab where they're ground up and extracted through a number of different standard procedures. Some examples of these are they may be steeped in alcohol or they may be boiled in water. And in the end you have this extract that is created, and these extracts are actually not one chemical, but instead are composed of hundreds of chemicals coming from each plant tissue. The library we've built currently has more than 1,400 botanical extracts, and this is from plants used for the treatment of infectious disease in traditional medicine. What is unique about this library is the fact that it's very targeted. This was not collected randomly. It was very intentional in which species we're studying. It's also highly biodiverse and represents species from many different families of plants and fungi. Now, in the laboratory, when we're looking for new solutions for antibiotic resistance, we have to ask a number of different questions. Those first questions are, number one, do these plant extracts actually kill or slow down the growth of bacteria? And this is a standard question asked by many people that study plant extracts. However, I think what's unique about our work and where we're finding more and more interesting data is we've asked other questions. If these plants don't actually kill the bacteria, could they be acting in some other way? In the past, many plants that were used for centuries in traditional medicine, but which don't kill bacteria, were viewed as old wives' tales, as nonsense or folklore. They were dismissed by much of the scientific community. And what we would propose instead is, instead of dismissing these, think about other ways that they might work. Could they impact the immune system of the host? Could they work by blocking communication of the bacteria? Could they take away the ability of the bacteria to cause harm or take away its ability to defend itself? And indeed, that's what we've found in many of our studies. I'm going to give you the example of Staphylococcus aureus. This is a pathogen that is a common cause of many skin infections. It also causes things like sepsis, infections of the blood, infections of the bone, infections of medical devices. In the US, 1 in 3 people carries this organism in their nose, and it can spread to the body when you have a compromised immune system. One of the ways that staph is able to be resistant is through the formation of this special community called a biofilm. If you can imagine for the moment, when you run your tongue across your teeth in the morning and you feel that slimy feeling, that is what a biofilm is. It's made by the bacteria. It's a mixture of sugars and other bacterial waste products that cause that to form. And this is what it looks like under the microscope. Okay. Now, one example of something interesting that we found is that in southern Italy, local people reported the use of this blackberry bush to treat skin infections. It was used especially for the treatment of furuncles and abscesses, so pustulent abscesses of the skin. What's very interesting about this blackberry extract is, as I mentioned before, it doesn't actually kill the bacteria, but instead stops it from forming that biofilm. And so if you look at this image, this is a confocal laser scanning microscopy image, and it's looking at the community of the biofilm. In the first column, you see what it looks like untreated controls. And the second column is a positive control, and then the third through fifth column is showing the drug treatment. And you can notice that there is a dose-dependent response. The green represents adherent cells. So as we reduce the response, you have more and more cells attached to this surface. In the presence of this plant extract, the bacteria are not able to attach. What does that mean? It means that we've taken away one of the key pathways that these bacteria use to defend themselves. When you take away their barrier, their shield, and their defense, it makes them more susceptible to your immune system and allows it to be cleared out. It also makes it more susceptible to antibiotics. In this study, we took IV catheters. These are the plastic catheter lines and when you're in the hospital and you have a catheter in your arm. And we cut these up and exposed them to the bacteria. In the first blue, you can see the control. There was no effect of the treatment group of just the extract in removing the adherent biofilm when alone. But what was very fascinating is that when you combine the extract with antibiotics, it makes the antibiotics work better. And so if you look at the purple line, this is an antibiotic known as daptomycin, and you can see just a small drop over control. But when you combine the extract plus the antibiotic, you get a much larger drop in the number of cells sticking to that catheter. So we're showing here that you can use plant extracts in some cases to improve the way the antibiotics work. Another major problem that is caused by this particular bacteria is due to its ability to create toxins. So bacterial toxins cause syndromes like toxic shock syndrome and the use of feminine products by women, scalded skin syndrome in newborns, which causes the outer layers of the baby's skin to peel off, and then abscesses and necrosis, which is very common in these skin infections. These types of toxins also allow this bacteria to invade your body. So they do this by evading your immune response. They can actually call your white blood cells to the cells, they get gobbled up, and then they release a burst of toxins to kill your white blood cells. This allows this bacteria to get into the body and spread very quickly. And so for a long time there was this idea of quorum sensing, which refers to the way that bacteria talk to one another. The idea was that if you stop them from communicating, can you make bacteria behave differently? Okay? And so the way that this is regulated in staph is through a two-component signaling system. Just to briefly give you an example from how this gene pathway works, it releases these little proteins known as auto-inducing peptides outside of the cell. When there are many of these peptides present, it triggers an event, a cascade of activity. This is the way that the cells are able to determine if they are alone or if they are surrounded by hundreds or thousands of their peers. When they recognize that they are together with a large population, they start to behave differently. They start producing more toxins, more things that can damage your tissues in your body. This brings me to another example. This is a plant from the Mediterranean, which you're probably familiar with. This is the chestnut tree, Castanea sativa, a very important edible plant. But we also noted in our interviews that local people would make washes of the skin to treat inflammatory skin disease with the leaves. Interestingly, we found that it does not kill the bacteria, again, but very uniquely targets this signaling system for quorum sensing and turns the system off. What does this mean in a real infection? Well, here we have an example of a mouse model. In this particular mouse skin, we have the bacteria is injected into the skin. It's an intradermal injection. And you can see that this large lesion forms. Now, if you inject the bacteria with a low dose or a slightly higher dose of this extract, you can see no lesion. There's a little bump because the bacteria are still alive. They're there. We're not killing them. But the lesion does not form because we've taken away their ability to damage the tissue. So it's a whole different way of thinking about how to address these aggressive infections. Another example of this similar pathway is from the Brazilian pepper tree. This is a plant from South America, but which is of course spread to the US and even here to the Mediterranean and into Africa as an invasive species. In traditional medicine, there are documents of this being used for a number of different topical applications, different ulcers, infections, and chronic wounds. Again, we found another group of compounds from this plant that do not kill the bacteria or slow their growth, but instead act by shutting down this signaling system. Interestingly, this extract also blocks biofilm formation, or the formation of that slimy defensive barrier as well. So in this case, we're attacking both the offensive and defensive mechanisms of this organism. We're currently working on isolating the active constituents. One of our key questions is it just one compound that's responsible, or are there many? And when you look at traditional medicine, oftentimes it's a combination effect of many compounds, either from a single plant or from multiple plants working together in synergy. So to study this in a very rigorous scientific way, we are working to break apart the formula and then study each part individually and then joined back together so that we can better understand how all of these individual pieces work together. One last example I'll give you before I finish is how can we look to plants to modify other pathways of resistance? Bacteria have several key ways of evading the way our antibiotics work. Some of them make it difficult for antibiotics to enter the cell. Others might result in alteration of the target site inside the cell. Efflux pumps can push the antibiotic back outside of the cell. And then there are some bacterial enzymes that can break apart the antibiotic. So one example I want to share with you is a way of using plant extracts to stop this process. So one of our most important classes of antibiotics are the beta-lactam antibiotics. These are important because they tend to have broad spectrum activity and generally they're quite safe. The beta-lactam ring is shown here in the picture in red, and there are a number of different bacterial enzymes that can break apart this ring. In order to look for potential extracts that can stop the breakdown of this ring, we tested our library of 1,400 extracts. In this case, we looked at just the 900, in combination with an antibiotic that the bacteria is normally resistant to. Out of this screen, we were looking for this concept of synergy. When we combine the antibiotic with the extract, do we get an improvement in activity? We found 25 extracts out of the 900 screen that showed some promising activity. And out of these, extract 649, and I can't reveal which plant it is yet because we haven't yet published this. This is new data. But do know that it is from a Native American medicine used again for the treatment of skin infections. What is exciting about this plant is that it reduces the concentration of antibiotic necessary to treat the infection by 1,000-fold. This is a huge improvement in activity, rarely seen even with synthetic drugs. So this is very exciting, and we're working on trying to identify which constituents are responsible. So in conclusion, I want to circle back to Hippocrates and note one of his other famous sayings beyond use food as your medicine is that the physician treats but nature heals. And this is a lesson I think that we can see since antiquity, that people have relied on nature to heal. And I want to pose this question: what is health? Is health bombarding the body with antibiotics that will wipe out all of your microflora and disrupt the gut? I would argue no. Perhaps the pathway to health is by restoring balance with these types of drugs that don't kill the bacteria, but just weaken them to the point to where your immune system is able to restore the balance. I think that's where the future of infectious disease treatment may go. So in conclusion, some of the questions that remain are: how can we use traditional knowledge of these remedies to innovate the next generation of therapies to help all of mankind? And how do we move beyond the 1940s paradigm of our definition of what antibiotic therapy is? Can we get beyond this idea of just killing the bacteria and move instead to these other concepts of restoring balance? Because I think that without the right questions, we won't find the right answers. I want to thank my team. I work with a fantastic group of students and physicians and researchers, and they really do a lot of work and have a lot of fun, I think, in the process. Thank you.